In our previous work, we reminded ourselves of what the definition of a definite integral was. You'll remember I made kind of a big production number out of the fact that it's not the antiderivative trick. The actual definition is you split the interval from a to b up into a number of subdivisions or smaller intervals, each of which delta x number I, which is supposed to be a positive number. Within each one of those, you evaluate the function at some point and then add up all such things and take the limit as all of the delta x's tend to 0. That's the definition. Right now, I want to concentrate on the specific situation. If the f of x is never negative for the x's that we're interested in, then because the widths delta xi are positive, then these products can never be negative. They must be 0 or bigger. So when I add up a bunch of things that are 0 or bigger, I get something like that, 0 or bigger. When I take the limit of such a thing, I can't get a negative answer by doing that. So if my function is bigger than or equal to 0 on the interval that I'm integrating on, it is impossible for the integral to come up negative. So file that fact away in your head. The way we usually calculate these integrals, if capital F is an antiderivative of little f, then we say that the integral is the antiderivative evaluated at the upper limit of integration, the one that's bigger, minus the antiderivative at the lower limit of integration. I'm saying that so that there can't be any possible wiggle room in our heads about trying to fix things up by making it a minus b instead of b minus a or something. In particular, I'm going to look at the function f of x equals 1 over x squared. That certainly can never be negative because x squared is never negative. An antiderivative is negative 1 over x. So thinking the way we were thinking just a moment ago, the integral from negative 1 to 3 of 1 over x squared, I'll take my antiderivative, I will evaluate it at the bigger limit of integration, the 3, and the smaller limit of integration, and subtract. When you put x equal 3 into the antiderivative, you get negative 1 divided by 3, negative 1 divided by x, minus, I'm going to take my antiderivative, negative 1 over x, and stick x equal negative 1 into that. When I do, 1 over negative 1 is negative 1, and the negative of negative 1 is 1. So then I do the subtraction, and I get negative 4/3, which is positive, of course, except that it isn't. Negative 4/3 is negative. But because of what we said before, if you integrate a positive function, you're supposed to get a positive answer. There's something wrong here. If you go back and review in the first semester, the fundamental theorem of calculus says this: if capital F is an antiderivative of little f, and the function that you're integrating is continuous on the interval that you're integrating on, then you can use the antiderivative trick. So the antiderivative trick is not always absolutely guaranteed to work. There are strings attached to it. And the one that everybody always forgets about is the part about the integrand being a continuous function on the interval that you're talking about. If you look at the graph of y equals f of x, y equals 1 over x squared, you see that it has a vertical asymptote at x equals 0. And unfortunately, we're integrating from -1 to 3. The bad behavior happens in the interior of the interval from -1 to 3. The function we're integrating is not continuous on the interval from -1 to 3. The fundamental theorem of calculus is not guaranteed to give you the right answer, and in fact, it doesn't in this case. Whatever the answer is, it can't be negative, but the antiderivative trick says that it is negative. There's no problem here. We're trying to apply a rule in a situation where it doesn't apply. But x equals 0 is the only bad spot on the graph of y equals 1 over x squared. Every place else, the function is nice and continuous. So here's what we're going to do. We're going to integrate over all possible x values except 1. We're going to leave the x equals 0 out. Now, how we're supposed to do that goes back to limits. As long as I leave x equals 0 out, I'm safe. So I'm going to integrate from -1 up to some number b. B is going to be negative, and in the end, I'm going to let b get close to 0. B will approach 0 from the negative side. Also, I'm going to integrate from a, which is some positive number, up to 3. And in the end, I'm going to let the a approach 0 also, except it's going to approach from the positive side. By doing the limit, the numbers that don't get included in the calculation become smaller and smaller as I let the limit be evaluated. When I actually do the limit, the only number that has been excluded from this calculation is x equals 0. That's going to be our trick. Let's look at the left-hand part first. I'm going to think of b as being a negative number, and mentally I'll think of it as being close to 0, because in the end, I'm going to let the b approach 0 anyhow. An antiderivative is -1 over x. Evaluate at b and -1, and you get the negative of 1 over b minus the negative of 1 over 1. 1 over 1 is 1. The negative of that's -1. And when you subtract -1, it's the same thing as adding +1. So if I want to integrate from -1 to 0, 1 over x squared dx, I'm going to take this quantity and I'm going to take the limit of it as the b approaches 0 from the negative side. This term, this 1, has no b in it. So the limit of that term is 1. I'm not concerned about that at all. B is going to be a negative number that's close to 0. So 1 over b is going to be a positive number. So 1 over b is going to be a negative number, and it's going to be large in magnitude. And then I take the negative of that, and I get a large positive number. And by making b small, I can make that -1 over b positive and as big as I want to make it. That limit doesn't exist. That limit diverges. That limit fails to converge. And the traditional way that people write that is to say that it equals plus infinity, which, as I've mentioned before, is not a very good way of thinking about this. When we write that, we mean that the integral fails to exist in a certain particular manner. It fails to exist because as I let b get close enough to 0, I can make these nice finite looking integrals as big as I want to make them, and the limit doesn't exist because plus infinity is not a number. If you want to think about this in the loose sense, though, what this says is there's more than 10 units of area associated with the left part. There's also more than 100 units of area. There's more than 1,000 units of area. Any positive number you want to pick, there's more units of area than that just with the left-hand piece. So in a certain sense, it really is true that there's an infinite amount of area associated with just the left-hand piece. Exactly the same thing happens if you look at the right-hand piece. You have the same antiderivative, negative 1 over x. I'm going to integrate from a up to 3, and then I'm going to let the a approach 0 from the right to exclude no x's other than x equals 0. When I evaluate my antiderivative, I get negative 1/3 plus 1 over a. Negative 1/3 is a constant. Its limit exists. That doesn't bother me any. The 1 over a is the deal maker. A is always going to be positive, and it's getting close to 0. So 1 over a will be positive and getting real big. I can make negative 1/3 plus 1 over a as big as I care to make it by making the a positive and close enough to 0. So using the same usual awful language, we say that this integral equals infinity. It would be better to say that it diverges towards infinity, but that's not how people usually say it. In any case, as with the left-hand piece, there's an unlimited amount of area associated with the right-hand piece. Since my function is positive, we interpret the integral as being area, so both integrals are equal to infinity, although that's a bad thing to say. So I had an infinite amount of area. I already knew I could think about the integral as being area. If I made the antiderivative mistake, if I failed to realize that there's a problem with the function I'm integrating, then we would be saying that the area, which we incorrectly calculated to be negative 4/3, and the true area would have to be equal to each other. And that statement, I hope by now, is obviously absurd to everybody. The problem here was I was using the antiderivative trick in a situation where it didn't apply. This number is wrong. Having said that, sometimes you get lucky. Whether the luck is good or bad depends on which way you want to think about it. I want to think about the integral from 0 to 1, 1 over square root of x dx. The thing that I'm integrating is continuous on the interval from 0 to 1, except x equals 0. 1 over square root of 0 doesn't exist. It's not a number. So I'm going to pretend I don't notice that, though. I'm going to pretend that there's no issue at all at x equals 0 and just grind away as usual. 1 over square root of x is x to the negative 1/2 power. The usual power trick can be used. Pretending I don't know that there's a potential issue, I'll stick x equals 0 and x equal 1 into the antiderivative. The antiderivative simplifies to 2 times square root of x. Put the 1 and the 0 in. This is 2. Now, if there was in fact no issue, I'd be satisfied with that. I would have convinced myself that this integral is 2, and since the integrand is positive, this would mean the area under the curve from 0 to 1 would be 2. But if I'm a little bit more clever than that, and I remember about the whole -4/3 thing, I'm not comfortable with this at all. So what would have happened if we had done it the right way? Instead of integrating from 0 to 1, I'm going to integrate from a to 1, where a is some small positive number. And then after I get that answer, I'm going to let the a approach 0 from the positive side. That's how we decided we were going to exclude everything except a bad point. We still have the same antiderivative. So I'm going to take 2 square root of x, put x equal 1 and x equal a into it. 2 times square root of 1 is 2. That's a constant. So I'm not worried about the limit of a constant. That certainly exists. 2 times square root of a, and I'm going to let the a get close to 0 from the positive side. If you remember what the square root function looks like, if I have a number a and I calculate the square root of a, as I let a get close to 0 from the positive side, the point approaches the origin, the y-coordinate approaches the origin. The limit as a tends to 0 from the positive side of 2 times square root of a is 0. So the whole limit exists and is 2 minus 0, which is 2. This is the same answer I got when I pretended that there was no issue. You might think that that's good luck, and in a certain sense it is. For this particular integral, if all I cared about was getting the answer, well, I got the answer. But on the other hand, as we saw with the -4/3 thing, it's entirely possible that I can grind my way through the antiderivative trick, get a number, and have that number be wrong. So we always have to be careful that our function is actually continuous on the interval that we're integrating it on. The other kind of improper integral we can look at is this. Instead of having a region of integration that starts at some particular a value and ends at some particular b value, so that the region of integration is the interval from a to b, and the integral is integral from a to b f of x dx, we could have a situation like this. We're going to start at some number a, and we want to include all x values that are to the right of a. The interval of integration would be a to infinity, and the type of integral we would look at would be integral from a to infinity f of x dx. Or to flip the picture around the other way, I want to include some number b, and I want to include all numbers to the left of b. The region of integration would be -infinity to b, and the type of integral would be integral -infinity to b f of x dx. Or obviously we can combine the two and have the entire real number line being the integral of integration, that is, which we would write as -infinity to infinity. And the integral we would give is integral -infinity to positive infinity, f of x dx. Now, infinity is not a number, -infinity is not a number. We can't think of finding antiderivatives and sticking infinity symbols into them because, as we've seen before, that kind of manipulation doesn't even make any sense. We have to think of having nice, regular old Calc 1 types integral and then taking the limits of that kind of thing. So for the first type, the integral from some number a to infinity f of x dx, what we'll do is we'll integrate from a up to some number b instead, some nice finite number b. We'll calculate the integral from a to b of f of x dx. This will obviously depend on what the b is. After we have figured out the nice interval, we'll take the limit of it as b tends to infinity, and in this way we will omit no x to the right of a. So this stays fixed, and this, in the end, ends up going off to the right. If I want to do the integral from negative infinity to b of f of x dx, the b is going to be fixed. I'll pick some a number less than it. I'll calculate the integral from a to b f of x dx, get a nice finite looking answer out of that, and then I'll take the limit as the a goes off to the left forever. These two things are going to be the definitions of these two types of improper intervals. For the third type, the integral from negative infinity to positive infinity, f of x dx, pick some convenient real number z and integrate first from negative infinity up to z in the way that we mentioned on the previous page. This is a limit of things. Then integrate from z to infinity, f of x dx, which is also a limit of things, and then add those two things together. If either one of these two integrals doesn't exist, either by going infinite on us or some other bad behavior, then we say the thing diverges or fails to exist. If both of these exist as actual real numbers, then we say that the improper integral converges or exists. I'd like to calculate the integral from 1 to infinity x e to the minus x dx. Parenthetically, if x is 1 or bigger, then x is certainly positive. E to a power is always positive. So if you wanted to, you could interpret this integral as the area of the region under the graph of y equal x e to the minus x, starting at x equal 1 and going off to the right forever. The definition that we said we were going to use is, I'll pick some finite number for the upper limit of integration. I'll do this nice regular integral. After I've got my answer, I'll take the limit as b tends to infinity. If the limit exists, if it converges to some real number, I'll say that this integral exists and converges to that same real number. Otherwise, I'll say the integral diverges. I need to have an antiderivative. If you look at x e to the minus x, obviously you could do integration by parts on it, and I'm going to be really lazy and do the tabular method. So I'll write the x first and the e to the minus x second. Derivative of x is 1, derivative of 1 is 0, and they're all 0 after that. Integrate e to the minus x, and you get the negative of e to the minus x. Integrate it again, and you'll pick up an extra negative sign, so that you end up with e to the minus x again. I'm going to multiply these two things together and add that term, so there'll be a x times negative e to the minus x running around. Then I'm going to multiply these two terms and subtract that. So I'll be subtracting 1 times e to the minus x, and all the terms are 0 after that. So this would be negative x e to the minus x minus 1 times e to the minus x. I thought it would be a little bit easier to think about if I went ahead and pulled the factor of negative 1 out of the negative x minus 1. Also, e to the minus x is 1 over e to the x. So my antiderivative is going to be the negative of x plus 1 over e raised to the x power. In my finite sized interval here, I've got to evaluate that at x equal b, evaluate it at x equal 1, and then subtract. The thing that I'm going to take the limit of is the negative of b plus 1 over e to the b. That's the antiderivative evaluated at x equal b, minus the antiderivative evaluated at x equal 1, which would be 1 plus 1 divided by e raised to the 1 power. After doing a little bit of simplifying, I have to calculate the limit as b tends to infinity of negative b plus 1 over e to the b plus 2 divided by e. The second term, the 2 divided by e, is a constant. It doesn't have any b in it. So when I take the limit of a constant, the limit of this term is just going to be 2 divided by e. At the moment, we don't know what the value of the limit of that first term is. In fact, we don't really know that it even exists. So we have to go off and investigate the limit of this term. If it exists, then I'm going to take whatever number comes out of this term, I'll add 2 over e to it, and we'll have our answer. If this limit doesn't exist, then I have to say that the integral diverges. If you look at the numerator, negative of b plus 1, as b gets really big, negative of b plus 1 gets really negative and large in absolute value, that is. The top tends to negative infinity. The bottom, e raised to a big power, is very big. The bottom also tends to positive infinity. The negative sign doesn't matter to me because I could pull it out of the limit if I wanted to. This is an indeterminate form, specifically of type negative infinity over infinity, but it's the kind of thing you can do L'Hopital's rule to. So I'm going to think of b as being the variable, and I want to do L'Hopital's rule to this. The limit of the term in question is the limit of the derivative of the top divided by the derivative of the bottom. The derivative with respect to b of the negative of b plus 1 is negative 1, and the derivative with respect to b of e to the b is e to the b. This is no longer an indeterminate form. The numerator, negative 1, is a constant, and as b becomes large, e to the b can be made as large as you care to make it. So the limit, as b tends to infinity, negative 1 over e to the b is 0. So that term whose limit we were uncertain about a moment ago turns out to be no trouble. Its limit is 0. So our integral from 1 to infinity, x e to the minus x dx, is 0 plus 2 divided by e, which is 2 divided by e. This is a very strange result. It says the area above the x-axis, below the graph y equal x e to the minus x, starting at x equal 1 and going to the right forever, is a finite amount of area. It says that the area is 2 divided by e. This is a very strange result. When you're dealing with infinity symbols in any way, you can expect rather odd behavior like this. Now, I made that small discussion about infinity not being a number the other day, and I've noticed many times people just won't listen to that. So what if I didn't buy into the whole infinity is not a number thing and just said, this is all silly. I'm going to find myself an antiderivative. I'm going to stick the number 1 and the number infinity into it and subtract. Well, we know the antiderivative, and I can't help but mention off on the side that this is wrong. What I'm writing down is wrong. Infinity is not a number. You can't treat it like a number. Generally speaking, it doesn't work. But anyway, I'm going to take negative of x plus 1 over e to the x and stick the infinity symbol into it. That would be negative of infinity plus 1 over e to the infinity minus, and then I'll stick the x equal 1 into it, 1 plus 1 divided by e to the x, e to the 1. Just as before, this term doesn't bother me. I'm completely fine with this. This one does bother me. Infinity over infinity, what's that supposed to be? And then I have to take the negative of that. This doesn't even make any sense. Many times people ignore all this talking and think that it does and say that that's 1 because you're taking something and dividing it by itself. Your area will then be negative 1 plus 2 over e, and if you check it, that turns out to be negative, which is obviously wrong because areas are not negative. What I'm trying to emphasize here is never do that. If you do that, you're showing that you haven't understood what the problem with the infinity symbol is, and that is a severe error. There is a lot of things you could say about improper integrals, but for our purposes, the reason that we're interested in these things right now is that shortly we're going to begin talking about infinite sequences and infinite series. And in one of those topics, there's a thing called the integral test, which will sometimes let us figure out where certain infinite series converge or diverge. And these improper integrals that we've been talking about figures directly into that. So what I've said here, I think, is plenty to get us through what we're going to need. So I'm going to stop on this topic. Next time, infinite sequences.